So, we're back with our favourite topic, calculus, and in this video we're going to be going through the proof of the power rule of differentiation. So I'm just going to remind you of the rule for differentiation which we derived last video. So you've got limit dy by dx equals a limit as delta x tends to 0, f of x plus delta x minus f of x all over delta x. There you go, you've got that limit there. So, what happens if we let f of x equal x to the n? Well, let's just sub that in here first. So you end up with a limit as delta x tends to 0 of x plus delta x, all of that to the power of n, minus x to the n, all over delta x. There you go. So, how are we going to solve this? Well, first, I'm going to focus on expanding this bracket using binomial theorem. So those of you that are unfamiliar with binomial theorem, it states that you've got a plus b power n is equivalent to a to the n plus n choose 1, a to the n minus 1 b, plus n choose 2, a to the n minus 2 b squared, etc. And you'll go all the way up to b to the power n. There you go, like so, with the power of a decreasing, the power of b decreasing, n always remaining the same, and the value down here that you're choosing increasing by 1 each time as well. So, how can we expand this expression in this case? So, you have let a equal x and b equal delta x. So then you have x to the n plus n choose 1, x to the n minus 1 delta x plus n choose 2, x to the n minus 2 delta x squared, etc, etc, all the way up to delta x to the power n. So what we're going to do, we're going to sub this into this formula here, give ourselves a little bit more space we had originally. Delta limit as delta x tends to 0 of x to the n plus n choose 1, x to the n minus 1 delta x plus n choose 2, x to the n minus 1 delta x squared, and etc, etc, all up to delta x at n. There you go. And all of this, oh yes, and don't forget the minus x to the n over n at the end there. Easy to do. All over delta x, like so. Now, notice that the x to the n's cancel on either side. So we are left with a limit as delta x tends to 0 of n choose 1, x to the n minus 1 delta x plus n choose 2, x to the n minus 2 delta x squared, etc, all the way up to delta x to the power n. And this is all, of course, over delta x. Excuse me for my awful fraction lines. Anyway, so now you'll notice that every term has a common delta x in it, so you can just cancel delta x from every single term out, which eliminates a fraction, which is extremely handy. So what we're left with here then, we've got n choose 1, x to the n minus 1, plus n choose 2, x to the n minus 2 delta x plus etc. And then you've got delta x to the power n minus 1 at the end there. So, what is the limit of this as delta x tends to 0? Well, every term, as delta x gets smaller and smaller and smaller, the value you're multiplying each term by gets smaller. So it's just the whole term itself is going to tend to 0. And again, if you sub in 0 here for delta x, it's going to be 0 times that term, which of course you know 0 times anything is just 0. So all you're left with is n choose 1, x to the n minus 1. What is the value of n choose 1? Well, n choose r is a number of ways of choosing r numbers from n. So you've got n factorial, this is the formula here, over n minus r factorial, r factorial. In this case, r is equal to 1. So you've got n factorial over n minus 1 factorial, 1 factorial. A factorial function is just effectively every integer up to that value multiplying itself together. So every integer, well, 1 is the first integer, like positive integer anyhow. So you're left with just dividing by 1, which is clearly just 1. You're left with n factorial over n minus 1 factorial. So what is that? Well, it's every integer up to n multiplying each other times by 1 over n minus 1 times n minus 2 times, and down to 1. You can see where this is going. And you can see there's the term common, here, 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 here. Everything cancels at the top, apart from this factor of n, which we're left with here. So you've just got n less. So nc1, n choose 1 is equal to n. So therefore, dy by dx is equal to nx and n minus 1. You'll find this is an incredibly useful. Oh, whoops, awful box there. Anyway, you'll find this is an incredibly useful result that you'll use extremely frequently in, well, basically most of differentiation that you'll cover. This rule is used in everything, really. So remember this result if you don't already know it. If you do already know it, then here's the proof. There you go.